Typically, he's a member of the high redshift supernova team, the one with the many prizes. But I won't say more importantly, but also equally importantly, I think Jason, at least for me, is ESO. Okay, so from the NTT all the way to the ELT, he has done pretty much everything. He was the VLT telescope scientist. He was there for the commissioning. He was leading the commissioning team. He's now the ELT telescope scientist. He was the director of the merged La Silla Paranal Observatory and many other things. But since he has so many nice things to show, I will stop here. I would just like to thank him very much. It's also a personal pleasure for me to have him here. So thank you very much for your time. Thank you for accepting the invitation. And the floor is yours.
It's a great pleasure to be here. It's always nice to talk about telescopes with people who like telescopes. I hope you like telescopes, otherwise you're in the wrong business, I think. Anyway, so I'm going to this talk is a very small scientific component. It's a lot of technical stuff. I still very strongly believe that astronomy is an experimental physics science. So knowing your apparatus is actually an important factor. It's not just trolling or the archive. So this is about the apparatus mostly, and a tiny bit about the science. So if anybody wants to run away, this is the time. Nobody will be offended. Okay, so corporate ESO does require that we show at least one slide about ESO itself. So we're the operator of ALMA on the European side. We run La Silla, which is an observatory with a couple of 4-meter telescopes, some 2-meter telescopes, and these days an ocean of little. I don't know this microphone. I have to talk into this, right? So yes, yeah, okay. These days, there's hundreds of little telescopes that people do all kinds of things with. The jewel is, of course, Paranal Observatory with the 4-unit telescopes and the interferometer, and then there's little things that collect around it also. Okay, so that's the corporate part. Okay, so the last one, which is the headquarters in Garching. So we're done with that part. Let's talk about the ELT. So to put everybody in the same frame, I think I'll have to be looking at this in here. Okay, it's a 5-mirror optical design. Basically, it's a 3-mirror anastigmat used on axis, and then you come out with a beam. This is not a weird design. If you're getting JWST data, it's exactly the same optical design that JWST uses. It's just that the corrector is buried further inside, but the steering mirrors, etc., are there. They don't do adaptive optics. But otherwise, it's a 39-meter primary, a couple of 4-meter mirrors, and the deformable and the M5 that get the beam out. Okay. We can't arrive today and not actually talk about the landscape in which we're landing, the landscape of JWST. So there's 2 options. One is we just give up. Okay? There's no point in doing anything. The sensitivity of JWST, there, for people who, my generation anyway, and as an infrared astronomer, I never considered that there was such a thing as a nano-Jansky. It's not a unit. It's a silly unit. Okay? JWST is actually observing in the nano-Jansky regime. They make plots with nano-Janskys versus wavelength. Okay, so the sensitivity is in a magnitude diagram here. We're playing here, so it's a different game. We have to actually accept this, and we're not going to get there. It doesn't matter how big a telescope you make. This is a stable PSF with a 0 background system. So as one strategy is you just outlive it. That's possible, but that's not particularly interesting. The other strategy is, of course, that you keep going, but then you have to be a little bit more intelligent is the wrong term, ambitious or accommodating. You have to think a lot harder about what you're doing. You actually have to find where you can. You're not going to go head to head with JWST. One of the things that this actually means is that the old paradigms may not be the right ones for moving forward. Now, this way that we've observed in the past may not be right, but that we will have to see. But both on the observatory, the operator side, and the community, the astronomers, the community, we may have to change our ways. And it may be that we have to go back to being much more experimental and not just data-driven, or it could go the other way. But being open for this is, I think, very important. Okay. I'm just going to pick one science case that I really like. Okay, my slides here are hidden by all kinds of other stuff, which is detecting intermediate mass black holes in globular clusters. This is a science case where angular resolution, really wins. Okay? So this is something that you cannot do within 6.5 meters in space, simply because your diffraction limit is not good enough for actually seeing things move. Okay? You can do it a different way. So this science case has been on the books for 20 years. I've been doing ELT since 2006, before that. So this is a long time. So people think of other ways of solving this problem. But fundamentally, you want to see the proper motions of stars in the center of globular clusters. What you can do, of course, is do it statistically with proper motions from HST, and this has already been done. If you have enough time in your telescope, the other telescope takes a long time to happen, the science case will be pushed by other places. But this is something that Mikado, which is one of our first light instruments, later with Morpheo as well, the multi-conjugate adaptive optics system, will be exceptionally good at doing. This is an imager and a spectrograph for a diffraction limit. Everything is diffraction limited, but for diffraction limited work. So a couple of milliarc second pixels. Okay. So a little bit, so that because the pictures, the graphic pictures are all very nice. You see this. This is really Morpheo. That's the cryostat on a crane going in. So it's a fairly big thing. That's at the Max Planck next door to the ISO headquarters in Garching. The D rotator is built. The filter wheel, that's really a filter wheel. This is huge. Everything is huge about this telescope, but it's still very impressive. 8 out of the 9 4K by 4K infrared detectors are already characterized and ready to be integrated. The 9th one is on the way. The 3 by 3, 4K by 4K each focal plane covers 58 arc seconds. So this is really a different problem. You can stand upright within the Mikado cryostat. I could stand inside the cryostat, so it's pretty scary. The other science case that I'm going to talk at that level also about is actually by taking spectra of transiting planets and actually seeing the lines move, you can actually see the atmosphere of the transiting planet, and you can actually also get depth information, etc. And this would be done with METIS, which is another first light instrument. These two are competing for which one actually is the first light instrument. This is a thermal infrared instrument working from L, so 3 microns out to 10 or so. This is also on a crane. But the instruments are on cranes. I think there's only one other thing where something is hanging on a crane. Everything else is so that's also being built. These are the sizes of this is the tip tilt internal chopping mirror. Other stuff inside the cryostat. It's I have to put my glasses on to tell you what's what. This is the derotating unit in lifetime tests in Garching in a cryostat. So all our instruments are not connected directly onto the telescope. They are actually on the Naismith platform and derotate independently from the telescope. So we do not mount them on some adapter and turn them. They're just too big. They have to be. Okay. So so now I'm just going to talk about the telescope. Yeah. So this telescope is very, very difficult. It's not complicated. People keep on saying things are complex or complicated. Okay? Complicated means that you're connecting nonlinear systems causally through each other. We have lots of nonlinear systems that are isolated one from another, and that makes it actually a difficult telescope because of its size and the number of things, but it's not necessarily complicated. We can choose to make it complicated, but that should be done after it's built, when you know which way, the right way to go. So there's a colossal effort in the design and in the concept and how we have thought about this telescope to actually keep it simple. And some of the things we often have had over the last 20 years saying, I have this clever idea, this would work much better, to which the answer is no, thank you. We'll do the dumb thing now. And it's not from lack of IQ. Okay, this is not the limitation there. The limitation is you do not want to make it complicated so that you cannot work out what's going on. Okay. A very nice, simple example in all of this is adaptive optics is built into the telescope. I'll explain a little bit why later. All adaptive optic systems to date deployed have been working in what I call a perturbative regime. So there's some kind of flat and you're working around the flat. So you can calibrate your system around this flat and you work around this flat. And everybody's happy because what you're doing is you're chasing the atmosphere. So that is basically on a Kolmogorov spectrum, it has no particular temporal, it has temporal and spatial frequencies, but it is a neutral structure. So you can actually work in this perturbative regime. The ELT adaptive optics system is actually fixing telescope first and not just the atmosphere. So your thinking is actually very, very different, and you have to protect the capability of the EO system to do that, and this will become evident in a few minutes. So if you go outside this regime, there could be this English naval thing, there'd be dragons out there, and none of us know about these dragons. So it's not an easy thing. Okay. This slide you almost see in all presentations of the technology or whatever of the ELT, something like this, is to give you a scale of the problem. So to work at the diffraction limit, your wavefront has to have an IPSC of about 200 nanometers. That's nothing to do with the size of your telescope. This is to do with how you collapse the wavefront. On a normal telescope, 4-8 meter thing, the deflections that your primary mirror has because of its support are of the order of a few hundred microns or so. The front surface has to be of in the nanometric precision, but the back is doing hundreds of microns, maybe a fraction of a millimeter, something like that. Okay? On the ELT, the back surface moves by 5 millimeters. So in this alone, we have 3 orders of magnitude larger problem to solve than a normal telescope. Now, I can give you other factors that combine in this way. From an operation point of view, 2 things happen. One is that, in effect, the ELT is 10 to the 9 times harder than an 8-meter telescope. And that means that it's not only a problem of scale and control, but it's also a dynamic problem in every aspect. There is no passive version of this telescope. We did not put adaptive optics in this to fix the atmosphere. You cannot build this telescope without being able to control all of these aberrations. The little movie that you see there, the deflections, this is scaled, there's a scale of 1,000 on that so that you can actually see millimeters over scales of meters. But these are the motions of the mirrors in the structure with the only variable being gravity. So the telescope is, if you go off, it is not something that is, a nice aligned telescope that has a little bit of coma and you fix this by moving the secondary and all this. This is a real beast. If that wasn't bad enough, behind me here is what happens to the primary when the air flows over it. So you put 1 meter per second. This is not some big, this is the air that you need to flush the primary so that it doesn't get hot air on it, etc. Okay? So that gives you a couple of microns of error, if low order error, just by ventilating the telescope. Again, I remind you, we have to have a couple of 100 nanometers at the end of the day. The high order part, you don't see in the low order thing, but that is also there, which is the pressure on the segments. And if all of that wasn't bad enough, on the top, over there, you actually see what happens to the primary when a cryocooler is working to keep the laser launch telescopes, the lasers that are in the launch telescopes, actually at the right temperature. So and that's a 1 Newton force. That is this. On the side, not even close, it's on the side of the telescope, and the transmission of the vibration gives you that on the primary. So it's a hard problem. Okay. So we knew all of this when we started. None of this is a surprise. So how do you go about deciding to build this thing, even to think, okay, this is stupid. You should not do this. It can't be made to work. But it could if you had an optical element that can actually fix all of these problems at the right stroke and at the right frequency. So the deformable mirror that is the M4, which has 5,000 actuators, is 2.5 meters, so that's more than my wingspan. 2.5 meter DM has 100 microns of stroke and works at a kilohertz. So as long as we can keep the aberrations in the telescope within the capture range of this mirror, it can be made to work. We don't need to treat it as a telescope. And we don't. From design all the way through to operation. We only care about the focal plane. We only care to be able to capture the focal plane on a wavefront sensor and have the vector of 4,886 actuation points for the M4, for the deformable mirror, within the ability of the DM to execute. Everything else that we do is a dance to keep the M4 happy. And this transmits on how the instruments work as well. And then we'll come back to that as well. So as I am repeating this many times, because sometimes overall it's a difficult thing for people to appreciate, the AO in the telescope is to make the telescope workable. The fact that it fixes the atmosphere is a bonus. It's not its major job. Its major job is to give you a diffraction limitable focal plane at the other end. Okay. So very quickly, because I said all of this, this test is this is a test that was done on the actual M4, there's pictures later, to show that the M4 really is 1 kilohertz actuator. This is the step function of, I think, what is it, mode 1 or something like that. So it really does work as a kilohertz actuator, and we do have, it has 100 microns of total stroke. We can actuate it in 10 micron steps. You can't give it a full 100 micron step. That's a force limitation on the system. It's not a mechanical. And okay, so some bad things. So this is all fine. Okay, everything will work. Somebody stands up and says all of these things, and everybody goes, yeah, it's okay. Somebody will do all of this. There's some things that we missed, and we missed them because these were not in our experiences of telescopes in the past. And this, one of them is a thing we call pupil fragmentation. You may have heard it as petalling or other things, etc. So on the GTC, the spider is about this thick. So when you actually try to sense the state of the telescope and you would put a subaperture or something like this about this size and you put a little thin stripe through it, you've made a little obscuration on an optical element. In tradition, you would get a diffraction spike off it or something like that. It's not nice, but nobody's particularly bothered. And compared to the scale length of the disturbance that you're trying to correct, which is about this big, this little thing in the middle is again a disturbance. It is not something that breaks the continuity of your sensing. On the ELT, the secondary mirror with its cell, etc., weighs 20 tons. So you're not going to hold it on a spider's leg, as literally we call them spiders because they were supposed to be so thin that they were like the web of a spider. It is, in the original design, it was 0.5 meter. We're now down to 200 millimeters, but 200 millimeters is 2 R-naughts of the atmosphere in good seeing conditions, about 10 centimeters, which means that this side of the mirror and this side of the mirror cannot be connected through simple interpolation. If it was 5 centimeters, you can go, even if you sense here and you sense there, you can actually join them with a straight line. If I gave you a data point on any curve here and the other one here, you don't know what's happening in between. If the frequency is fast enough, you're stuck. So this is pupil fragmentation. Depending on how you sense, you can get into trouble or not. So one of the things that can very easily happen is that an error in your reconstruction of how this is happening will imprint on the weakest mode of your correction. So you correct in all kinds of modes, but the weakest one is piston, because all the other aberrations stay put. The only thing that you've done is stepped your wavefront. And this is irrespective of anything else that you're doing in the system. This can happen. And it happens on 8-meter telescopes. If you have very high resolution and you get it wrong, you can actually see the VLT does it. It's referred to often as the low wind effect. There's all kinds of words like that about it, but those are the triggers. The physics behind is that you actually have disconnected information, and you cannot connect it just so easily. So one of the ways that you can fix this, sorry, before I go to fixing it, this is just say, okay, but if you step, you would actually see it somewhere. You would see it on the footprint of the M4. You would actually see that something was going wrong. The picture on this side, everything is flipped. On this side is the surface of M4 when you're correcting perfectly to the diffraction limit, because there's atmosphere, there's telescope, there's all kinds of things in there, and that's the surface. The corrected wavefront is the next one. Now, if you say I'm going to see the petaling error in the M4, you have to see that one in there. And that signature is not clearly visible in there. So you can't just say, where's the mirror? I will see what's happening. And also, it could be on purpose petaled because of other reasons. So the way you can fix this is, instead of running a geometric sensor like a Schack-Hartmann, you'd run a pyramid, which is actually an interferometric sensor. So you would sense the difference between the petals, because there's an interferometric signal. This is okay. So you can run a pyramid and everything's okay. The slight limitation there is that the pyramid has to be working at high stress to sense it. You actually have to have coherent photons in order to interfere. The ocean of photons doesn't, the incoherent photons don't do, well, they actually spoil it, but you do need coherent photons. So unless you have enough coherent photons, you're not going to get the interference signal, which means that you need to have decent Strel ratio. Decent Strel ratio comes by sensing in the infrared. That also helps because our note is bigger, but it is not there in the visible. So you actually have a trade to make as to how you're going to manage this, because the instruments want to observe in the infrared. They don't want to sense in the infrared. They want to sense where they're not observing, but the signal is best in the infrared. So this is just a plot which shows you how bad it gets with changing Strel. I can talk about it if anybody has a particular question. What you can actually do is have a second sensor, which is this is a dispersed fringe sensor. There's one of those in flying in JWST. This is not a new thing. This incarnation is by a chap called Sebastian Heffert. He was at the University of Arizona when this was done. He's now a professor in Leiden. And what you do, you can actually see how big it is. It's only about this big. It's not a big thing. But you actually imprint little transmission gratings on the different petals, and you create little spectra from the interference of this one with this one and this one with this one, and you do your different baselines, and that's what you see in the picture there, the little spectra. And I think on the right, yeah, there you can actually see the gratings. It's dirt cheap to make, really relatively straightforward to put in, but it does need that your petaling is reasonably stable. It's not going to chase petaling at 500 hertz. So we have various solutions, but this is a very real thing. Okay. I think this is the last slide before I just show you pictures of big stuff. So the rest of the talk is literally going to be, here's another big thing, here's another big thing, here's a shiny thing, here's a big shiny thing, it's various things. But so don't worry, this is the last one. And I know there are a lot of words, but they're mostly for me, not for you. Already for the VLT, since 98, we run in permanent closed loop. We have 100 years of 8-meter operations now on Paranal. All 100 years of 8-meter operations are in closed loop. It is not, there's no ballistic telescope. There's no telescope that's just drifting somewhere. You know, it's a good telescope. The way, you know, you go to a 4-meter, you point, and, you know, you may guide once a second or once or whatever. This is not the case. On the VLT already, you manage the focal plane. It is not where the telescope is pointing, the focal plane, and you are permanently wavefront sensing and fixing the primary every 60 seconds or 45 seconds, depending on what you're doing. So this is what we do. The only difference between the VLT and the ELT would be that you would actually do this not just for tip tilt and for the aberrations slowly, but you'd have to have 50 modes that you'd be running at 500 hertz, and then the instrument. So one of the big things that, so in terms of telescope operation, it is just a deviation from the model that we're already running. In terms of instrument operation is radically different. The telescope is not a participant in the operation of the instrument, only the info. So the interface between the telescope, the instrument, and the other side is a vector of 4886 aberrations. That's all they send. There's a bit about, I want to point at that star or that star, but that happens once an hour and nobody particularly cares. It's something we all do. But the actual handling of the focal plane is done by the instrument. So every instrument has a pyramid in it. Some have many Sharp-Harmans, some have pyramids and Sharp-Harmans. They have different combinations, but they hold the focal plane. Okay? But not the rest of the telescope. You just say, the only thing that you can talk to is M4. Our business is to hold the rest of the system. Now, that basically means that anything that the instrument does not sense will not be corrected. So the instrument has to know what it wants to do. There isn't somehow magically somebody is doing something for you. The only thing we do is keep M4 happy. Okay. So, as I said, ELT is a dynamic task. So now, status and pictures we're doing. Okay, not so bad. I have lots of pictures. Evanthea will stop me if you've seen enough pictures, or somebody stop me if you. So we are beyond the 70% earned value of the system. So we have contracted 95% of the cost of the system, and we have received in goods and value 70% of the project. So 70% of the actual work. This is the way project managers count things. You know, have I paid? And we don't pay unless something's been made. So it doesn't. All the things that are green in the first column is design contracts that have been completed in design. The next column is manufacturing, and the last column is, I think, whether it's on the site or not. I can't read it up there, and it's hidden here. Okay, and the words there are all the same words that you're going to get later. The telescope is within 10% of the budget that we declared in 2014. And in terms of money, we are 3 years late compared to where we expected to be. This can sound really weird, but Thankfully is the wrong word to say about the pandemic, but the two of the 3 years can be attributed to the pandemic. It could be that if pandemic didn't happen, we'd still be 3 years late. That's a different statement. But currently, we are. If we take the timeline and we say 2 years, which is justifiable somehow lost due to the pandemic, we are 1 year behind schedule and actually 10% within budget, which is, I think, quite remarkable. I don't know any other, either the original cost estimate was spectacular or the guys doing the job now are spectacular or both, but this is, at least in the ESA experience of our own project, I'm not looking at anybody else. Our own projects have never done this. So it's pretty good. Okay. So some stuff now. This is a movie that I hope will play. No, it will only play if I click. The reason I'm showing this movie, which is a lot of cranes moving around, et cetera, is because there's 2 events in this which are actually quite important. The sun sets, it's a normal place. There's this comets. But there's a lot of cranes moving around, but there's two moments where this becomes particularly interesting. One is coming up now. You see the dome actually turns. Now, it's not turning on its motors, but it is actually turning on its bogies. Okay, so they're not powered. It is turned by pulling it on cables, but it actually does turn. The other thing is, there you go. The other thing that you're going to see, this is quite remarkable. This is an 80-meter diameter steel structure that has just been put there. The other thing is now you're going to see the doors move. And it's very difficult to convey just how enormous these things are. The doors moved on their own motors. There's no other way of doing this. So from a telescope point of view, and this is a moment of great relief, because this is really a very, very big thing. And the only thing the doors in a dome really have to ever do is just close. You just close. The other things that they do for opening for the astronomers and all of this other stuff is good. But protecting the thing, it means they have to close. So they close. So this is very nice. Okay. So now a couple of things. I know we're not there, but this is a map. This is a seismic map of the world. And red is bad. Other things are not so bad, but red is bad. So if you're going to pick to put an observatory, you'd go like, you must have a really good reason to not go there, because that's where we are. I think there are redder places, but I'm not sure this map has got the right color code. So to go there, we actually decided to seismically isolate the entire telescope. So the dome itself is a normal building. So normal buildings in Chile are all seismically isolated, and every hospital, every police station, every school, these are all seismically isolated. This is a normal thing. There's nothing weird. This you do with things like the black thing on the side, which allow you to move sideways. So the ground moves sideways, the building on top doesn't go anywhere. Everybody's happy. That stops the building going sideways. But the telescope also has to stop going up and down. And this is done by the other devices. The reason these people are there, Gianluca, Adam, Javier, Jan, is that to give you the scale of how big these devices are, which literally separate the telescope also in the vertical direction. So this whole thing is fused. So in a normal configuration, the telescope is as stiff as anything, normal, as if the concrete went down into the rock. And if there's an earthquake, the fuse blow, and this enables, and then the telescope is floating on this, and you don't get accelerations you don't get significant accelerations transmitting through the system. This actually was significantly cheaper than I thought it would be, and it allows us to actually take the maximum acceleration that the telescope experiences to well below the one that the VLT was built for. So from a seismic acceleration point, the mechanics above this system are actually easier to do than building the 8 meters. And the earthquake accelerations for this are significantly high. Okay, so first things first, no power, no telescope. This is 5 megawatts of solar power installed actually with a deal through us by the energy supplier. So it's actually run by the energy company, not by us, but the only client in the middle of nowhere, the only client is us. But there's a grid line that comes up, this feeds into the grid line, and we go out of the grid. Because the grid is not remarkably reliable and other things, we're at the end of a line, it's not particularly good. This is a 5 megawatt UPS. So these are containers, you buy them, we have them on Paranal as well. This is a new technology, we didn't have it original Paranal. It's a flywheel, the power goes in and drives the flywheel, and there's a diesel on the other side of the flywheel. So in case the power is not, the power that we get is from the flywheel. We never see the grid. So the grid can oscillate as much as like, we just get the flywheel. If the grid falls, the diesel starts, continues the flywheel, we don't see anything come out. So this we call a power conditioning unit, and this is our power conditioning unit on the mountain. It's a 5 megawatt UPS. Okay. The second thing is, whenever you give one of these talks, the software guys never get any credit. Afterwards, they go like, but we're doing all this work. Nobody ever says anything. So it comes up front. Yes, we're writing a lot of software. Yes, we have a lot of control. There's a lot of simulations. We have a mock control room in the integration building in Garching. These guys are looking into the test stands, and 5 there in test is clocks, etc. So I've done that bit so they don't get angry. Let's go quickly. The dome is about the size of a football stadium. That's the Allianz Arena with the dome in Munich. They put 70,000 people there, and they watch 22 people chase a ball. We put a telescope in. I think my solution is better. Some pictures of the dome and the doors. This is just big stuff. I told you the rest of the talk is just big stuff. This is big. Okay, it's really big. If I stand next to the dome drives, I think I can just about peek over that thing. So that's basically a 2-meter size boogie that drives the doors. You look down, it's a long way down. So kinds of things, ventilation, things, etc. This is an electronic engineer super happy that the computer room floor is going in. This is the computer room in the dome. This is not the computer room in the control building from where it's going to be run. This is only for the field electronics. The actual the computers that are telling these computers to do something are somewhere else altogether. So this is a pretty big thing, and this is now finished. And I think Andy Wright is now there to start putting in cabinets. So it's happening. This is the telescope. We call it main structure. You can call it mount or whatever. That's the state in January when I was there. You actually can see that it's pretty much, so the azimuth is all done. The altitude is still on the jacks. The telescope is actually on the pads right now for the azimuth. You see that the Naismith platforms are not there. And that's because the Naismith platforms in this telescope are just self-standing structures. The telescope is not buttressed by the Naismith. It is actually a standing thing, and then you put the Naismith platform on top. And that's a design decision, also part of this concept of how you operate and how you detach the focal plane from the telescope. I told you this is an f.9 primary. You don't get a feeling for what that actually means until you stick your head out. I've got a picture with me sticking my head out, but I look remarkably stupid, and maybe it's my normal look, but I don't particularly like it. That block there is about the size of my head. So this is really steep, and you don't notice. Even if you had a smaller one, you wouldn't really notice it because it's not on a human scale. But f.9 is really, really steep. Okay. More pictures of the telescope, the adaptive relay tower in there, the mounts for the lasers on the side. This is, if you've been to the GTC and you've seen the gap where the segments are and you crawl around to try and get, this is the equivalent space for us. The segments go on top of this. It's a long way to walk. So we actually decided that you would be able to walk. because actually that, and also we hired a guy called Tucker Booth, who is significantly taller than me. And he says, okay, we'll make it okay, so that he has to go like this, but he doesn't have to crawl. Okay, so it's really more telescope, fine. Now M1, I won't go through this slide because it's really how you make the segments, you cut and polish, etc. I'll just show you what is this? Yeah, lots of pieces of glass. There's a lot of glass, 798 segments in the mirror, and an extra 7th sector, so that when you coat, you can exchange a fresh piece. You don't have to recoat the same one that you have. We actually have destructively tested some of the segments for vibrations. This is not with the glass, this is with an aluminum thing. There's a movie here, but since the sound doesn't play, or we won't play the sound, but if you were hearing it, you'd hear, bang. And what that is was one of the motors actually snapped, and we went and found the weakness and fixed that. So we're doing weird things. Segment with all its supports. This will be kind of familiar for people who've seen the GTC ones. It's very close. We've hired a whole bunch of people from GTC over in Garching. So you want somebody who knows what a segmented telescope is. We didn't. So you hire some people who do. So we hired some people from GTC and here. Okay. There's coating chambers on Paranal already working. It's nice. It's another segment. This is a shiny segment. We're coating everything with protected silver, apart from the M4, which is still aluminum. There's a reason for that. I can tell you in if there are questions. Okay. So there's 798 of these things that have to be put together. This is a warehouse on Paranal, where we put, once the segment arrives and it's been tested and certified and blah, 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 and coated, it goes back in here. And that was, this is the bodega right now. We've actually, if you see there's some segments on the floor, the bodega is full. There's over 600 segments on the mountain waiting to go into the telescope. Okay, so we are actually accelerating the acceptance of some other storage places, because Sagem is at this point, I think, generating a segment every day or every 2 days. So it's a lot of segments. Okay. Another coating chamber. I don't think people are excited about it. Coating chambers, I am, but it's okay. These are our actuators on that side, and our edge sensors. We have capacitive. You have capacitive edge sensors. We have inductive edge sensors. They're supposed to be less sensitive to humidity. And they're also sensitive to shear and gap. The capacitive ones sensitive to the dihedral angle, which is the same thing. You can reconstruct for both, but okay. We test all of this in the lab in Garching. So this is one flower, we say, of 7 segments. You go together. Okay, then control. This is literally running those segments against the edge sensors in closed loop. So we have to change 2 segments every day. So otherwise the downtime comes too large. So there's a segment manipulator that picks up, goes on a crane across the primary, turns, picks up, pushes the segment up, picks it up, gets it out. And we spend a lot of time worrying about detecting errors in the thing. So if you have one segment that is actually wrong and you don't detect it, because it imprints its error in the control loop, you end up, which goes with the number of segments that you have, you can end up with huge amounts of astigmatism in the mirror. So you actually have to detect errors and fix it. And this is just a slide showing that we have the software and the analysis to do that. We have another thing, which we call the phasing gun, or local coherencer, which is made, this is in EDOM in Bilbao. It's a little interferometer that gets picked up by the same thing that picks up the segments, flies over the segment, and then looks at the edges of the segments and tells you where the segment is relative to its neighbors when it comes in, so that you can accelerate phasing afterwards. Okay, leave that aside. Is the other thing that's on a crane. This is the secondary mirror at Sagem being driven over, whatever you want to call it, to its test stand. I'm not going to show you the whole movie, but I'm going to show you this. This is the most beautiful piece of glass I've ever seen in my life. I think I kind of say this about pretty much any piece of glass that anybody shows me, but this one really does deserve this. I think it's very difficult. This is a 4.2 meter convex mirror that's going to be hanging upside down, 60 meters in the air. And it is, I don't know, it's brilliant. Somebody made this for me. It's cool. Okay. This is the cell in which it's going to be made. So all our glass, I think all our glass is from Schott. It's all zero dio. I think it's Philippe maybe. I think it's all. And it's all almost all polished by Safran in France. This is the cell for the M2 or the M3. They're identical. At Sener outside Barcelona. This is it with its the dummy mirror on. There's a stand. It's the whole cell on the stand. So this stand rotates so that you can do all the gravity orientation. RM3 at Safran. It's a 4.2 meter concave, mildly spheric mirror. We want, but you get into this insane thing where you think this is, it's okay. We'll leave it till later. It's okay. It's not a. When you have the other problems, this looks easy. It's not, but it looks easy. Okay. This is Elise Vernet and a mirror. That's the M4. The glass is not connected. There's another one that's connected. I don't know, how big is your DM in your, I think it's about this big, right? Yeah. This is 2.5 meters across, and you actually have to have Vernet, Elise there for scale. It's quite an incredible thing. Here it is in Bolzano in Italy. Roberto Biasi, who's the CEO of Microgate, one of the two companies that are working on this, calling Adoptica as a consortium. That's the back of the mirror. And the little movie there, you can actually see some things getting brighter and fainter. That's actually poking the mirror. That's why I showed you the other thing. This is actually, at this point, it's operable and functional, and in almost every respect performant as well. It will all be tested on a tower. That entire tower then goes to the mountain and is actually located inside the dome as well. The M5, this is the nastiest piece of glass that we have. It can also become beautiful, we hope. This is made out of silicon carbide. So you actually have to make it in these pizza slices and then stick them together, braze them, and then polish it. And there's all kinds of stress that are induced. If you think about this, there's a piece of silicon carbide, and then you put a layer on top of it, like a coating in a mirror. Okay? The coatings in the mirrors, even on GTC or an old telescope, actually stress the glass. So in the error budget for the segments of the ELT is the coating and the change of the shape of the segment due to the coating. This happens here as well. The pieces stress. So when you connect them and then you polish, you're actually relieving the stress in the piece, and it has to go somewhere. So this can actually lead to things breaking. So this is actually, it's been a very difficult piece. But there it is in the test setup, and this is the mirror against Safran, with it being shiny. It's not yet polished perfectly, but it is already shiny, which is very, very, very good. It goes on a stand. This is in Sener with its dummy. The whole stand goes to Garching, and we test all kinds of things. This thing tilts at 100 hertz. And so the formula goes at 500 or kilohertz. This goes at 100 hertz. Okay. Just because we're having trouble with the silicon carbide and we're not sure how it would go, we bought a lightweighted zero-dio glass blank. It's smaller. It has the same mechanical properties as the silicon carbide, but it is a 1 arc-minute field of view, not a 5 arc-minute field of view mirror, which we're in the process of trying to get polished in the north of Wales. There's an adapter. I think you call it an A&G unit. It's the picture on the top is not a joke. The plane, I came from Munich in an Airbus A320. That's an Airbus A320. The fuselage, so I could sit there, 3 in a row, somebody pushing a trolley of food between us, the bags underneath. The wings don't fit through. This is fair enough. But everything else goes through our adapter. That's the size of the thing. And there it is outside Bilbao. These mirrors all move, the arms move, etc., etc. So each guide probe has a Harman and an imaging camera that can work at 500 hertz, both of them. So it's a full, every arm, there's 3 arms, every arm is fully AO capable. So this is my last slide. The we there is a little bit of a royal we or whatever, but I think it's fair to say. Let me put it, I expect the telescope to move this year. So the azimuth will certainly be moving. The pads have been cleaned, everything in the summer. Altitude should move by the end of this year. Okay? That means that we expect to be putting in glass next year. Okay? And first star, so that's when we actually see light coming through the telescope, is either at the end of next year or in 28. Okay? So first light, which has a very formal definition, etc., is currently scheduled for, I think, the 31st of March 29. That is 2 months after I retire. So I would like to see the other stuff before. It is actually when Roberto Tamayo was the project manager at the time, so I think maybe that's a different thing. But first light by Q1 of 29 is, I believe, very realistic. I'm always very cautious with schedules, but where we are, what we see, the glass will have. So the released instrumentation then is that year, and then there's a commissioning of instruments, etc. The current schedule of the project is not currently driven by the telescope. It's actually driven by the instruments. But first science is expected in 2030. And I think I'll stop there. Thank you.
Thank you very much, also for a really interesting talk on this incoming ELT. So do we have questions from the audience?
So thank you for the talk. One thing I wonder is how many people are expected to be operating the telescope during the night?
That's a very good question. I don't know what you mean by expected. On Paranal, when we're running Muse, which has 4 laser guide stars, the full AO system, whether it's in LGAO or LTAO mode, whatever it is, I can't remember how many spectrographs. Muse has 12 spectra, etc., etc. There's an operator and an astronomer, and there isn't somebody else sitting somewhere else. So if you can get to that stage, this is no different. The question is, how long does it take you to get that stage? Or do you even, that's my early comment, do you even want to be at that stage? So if you think about this, if it was a high energy physics experiment, you would not go to that stage. You'd have an army of postdocs and an army of grad students all operating or interacting with the apparatus, because that's also part of executing the experiment. This is a cultural decision as to how you run. It is not a technical one necessarily. Technically, you should be able to just push a button and it will work. That's what we've designed it for. Is that the best thing to do? I don't know. I wouldn't like to work that way, but then again, I'm weird. So, but fundamentally, the control room is on Paranal. It's got a console the size of one for the UTs, and that's it.
Maybe I'm wrong, but the question, I think it would be, how many engineers will you need during the day to do the maintenance of the telescope?
So we did this, we've done this repeatedly over a number of years, where we actually count how many hours of work you have. One of the interesting things on with Paranal is that you actually, because there's lots of telescopes, you actually have real optimization in number of people. So every observatory has an expert control engineer, but they only need it once or twice. Okay. On Paranal, you have 2.5 expert control engineers because they're used all the time. So the same thing happens here. So we think that the equivalent, whether it's engineers, technicians, etc., it's about 130 people, which is the same as running Paranal. Whereas contractors, staff, what the mix is depends on what is procedural, what is not. But that's been a steady number. It may go down, but it is about that. But that is, it's not 130 people in at Calp. It's 130 people at Roque. It's not they don't drive up in the morning and drive down in the evening. They're there at 8 o'clock in the morning and stop when the sun sets. The hour, and that's dictated by hours. It's not if efficiency of this many hours are needed. The schedule of the 24-hour activity of the telescope is dominated already on Paranal by daytime. It is not dominated by what the astronomer wants to do, which button. That's fairly easy. It starts at sunset and stops at sunrise. That's isolated. The work that makes that capable is the other hours.
Yeah. So you were presenting also what was the strategy adopted for ELT, and I guess that all the next 30-meter telescope will also have the same challenging that you were showing, right? And do they apply the same strategies and adopted for the ELT, or what is the difference?
Okay, so there are two different things here. One is the Giant Magellan Telescope. So we'll keep that aside because that has a particularly different problem. TMT, at least originally, is running in the baseline, as far as I know, is running on a fixed secondary, so a active but not adaptive secondary, although they're now exploring an adaptive one. And then Nefarious, which is a very, very powerful post-focal AO system. But one of the problems of having a mirror that is this big, even with a very high density of actuators, is that you don't get stroke out of that. Okay? So you have to get your telescope to the state that it can be digested. So one of the reasons, in the sense that TMT stays, if I were told to build a 30-meter, possibly I'd do that too. Because you can stay there. It's hard, but you can stay there. But I wasn't given that option. I was told at that time 42. At 42, the deflections are such that you cannot go down that mode, the focal plane. So TMT, I think, now that we have shown that you can get a 2.5-meter deformable, are exploring a deformable, and then that will be really powerful. GMT has a separate thing. They have 7 deformable mirrors. They do all of this, but because the gaps between their segments are significantly larger and their segments have very different mechanical properties to the stiff things that we live with, the challenge there is a co-phasing of basically 7 telescopes, not co-phasing of mirrors, which is a different strategy.
Thank you for the talk. Everything very impressive. My question is, what instrument will you use for, not for first light, but for commissioning the telescope?
Okay. Yes, that's
Metis or Picado?
No.
So you have your own.
So I've missed, I don't have this in this thing because usually we give this presentation as a double act, and I have a colleague who actually presents the phasing and diagnostic station. So the beam comes out of the telescope. There's a pick-off mirror, theoretically to go down to Coude, but on the Naismith platform, we have a thing that's about size of this table a little bit bigger, in which we have a modified Shahaphan a la GTC. We have a infrared pyramid. We have a 1 arc minute imager. We have an infrared Zernike wavefront phasing camera. We have a guest port in case somebody comes up with a clever idea, and a diffraction limited infrared imager. So we have a Swiss Army knife there. We don't know which problem we're going to be solving. So it's my analogy there. You have a Swiss Army knife. Nobody ever uses this saw. They all have this saw. I've never seen anybody use the saw, but if you knew you need to cut a tree, you just get the one. So we have that, and that is for commissioning, and it actually can do everything, including the infrared pyramid. That doesn't mean that we've solved all the problems for the instruments fully, but including the exchanges, etc. So that's all done with that. We don't wait for Mikado for commissioning the telescope.
Okay, any more questions? Oh, okay, last one.
Sorry, already over time, but just very quickly, could you quickly go through the instruments that are maybe planned for the ELT?
So we have Mikado, which is an infrared diffraction limited imager with spectroscopy as well, and they're putting an IFU in it. We have METIS, which is a thermal infrared imager and spectrograph at high resolution spectrograph in the mid-infrared. There is Morpheo, which is the multi-conjugate adaptive optics system. All of these things are running, so they are approved and funded and running at different stages. There's Harmony, which is actually went a very long way. Everybody decided that it would be better to take a step back and kind of push again, because we were in a very, you end up going down rabbit holes, and it was a bad rabbit hole for everybody. So somehow it got out, which is basically an IFU, an infrared IFU. I call them eNACO, eVisir, for people who know the VLT instruments. We have eNACO, eVisir, eSymphony. Then there's the wide field, what's it called now? Does anybody remember what it's called? Doesn't matter. There's a multi-object spectrograph that is in construction, which uses the whole field. There's Andes, which is a high-resolution spectrograph from visible all the way to infrared with 3 separate spectrographs. Those are all approved. So the money is there. There's consortia that are going. They're just at different levels of progress. Things hanging on cranes are the ones I showed you. The other guys don't have things to hang on cranes yet. It's okay. And then approved, no matter, so it's in the planning, it is approved, but it's waiting until we know the state of the telescope before you get going, is the planetary camera, the one that looks, the ultra high resolution system, because unless you know what the telescope is doing, there really is not much point in starting that, because you just can't be solving the wrong. This is really solving the problem. So that's also approved. All of those things are running. Then what happens in second generation is open. ESO has various open calls at this point. What should we do next? And how should we think about things, et cetera, which is running. I know it's called some Horizons thing that's past my retirement, but the first 6 things are in train with the train in different stations right now.
Okay, then I think we can thank the speaker again. And there should be now coffee at the cafeteria, so please go ahead and then you can keep asking questions. And for the students, please go over so I can take note of your attendance.